Unit 3, Video Lecture 3, Atomic Mass and Weighted Average. Before we start, let's talk about the difference between mass number and atomic number. Remember, the mass number is the sum of the protons and the neutrons. The atomic mass is the weighted average of all of our naturally occurring isotopes. So which one do we get from the periodic table? That would be the atomic mass. Remember, in our periodic table cell, so 6C 12.01, 12.01 is the atomic mass of carbon. If we take 12.01 and we round it to the nearest whole number and get 12, this 12 is the mass number, the sum of the protons and the neutrons. Let's take a look at some examples of different isotopes. Hydrogen has one proton. Recall the protons have a mass of 1 AMU, so this atom of hydrogen has a mass number of 1 AMU. However, hydrogen that has one proton and one neutron, each having a mass of 1 AMU, would give us a total mass of 2 AMU. And finally, we can have hydrogen that has a mass of 3 AMU because of the one red proton and the two green neutrons. Helium has two protons. So 2 protons and 1 neutron, this helium would have a mass of 3 AMU. Notice here we still have the 2 red protons, but now we have 2 green neutrons, so we have a mass of 4 AMU. Notice here that the number of red protons always remains the same. The number of protons is the atomic number, and the atomic number gives us our chemical identity. If we look at lithium, what would the atomic number of lithium be? 3, because in our two examples of isotopes, we're going to have 3 red protons, and in this case 3 neutrons, here 4 neutrons, giving us a mass of 6 AMU or 7 AMU. Here we can look at two examples of carbon. Carbon having 6 red protons and 6 white neutrons, we can get a carbon atom with a mass of 12. Another isotope, carbon-14, still has 6 red protons, but here it has 8 white neutrons. So if we had to talk about what an isotope is, an isotope has the same atomic number, a different mass number, and it gets a different mass number by a different number of neutrons. So how can we distinguish one isotope from another? Here, looking at carbon-12 versus carbon-14, these numbers on the top are going to equal our... So how can we write, what's a way that we can write to distinguish isotopes from one another? If we take a look at our way we're writing here, we see carbon-12 and with a 12 and a 6. This top number is the mass number, and this bottom number is the atomic number. This is called isotopic nomenclature. Nomenclature refers to a naming system, so this is a way that we can write and name our isotopes. If we look at two isotopes of silver, we see silver 10747 and silver 10947. These 47s on the bottom are the same because these are our atomic number. This is our number of protons. Our 107 and our 109 are our mass numbers, the sum of the protons and the sum of the neutrons. One of the nice things about writing elements in isotopic nomenclature is it's very easy to figure out the number of protons, because it's 47 for both of them. The number of electrons is also 47 because the number of protons and the number of electrons remain the same. And setting it up this way, if we simply subtract 47 from 107, this silver atom has 60 neutrons, where if we take 47 from 109, this silver atom has 62 neutrons. So let's take a look at three naturally occurring potassium isotopes. Well, potassium, if we look on our periodic table, has an atomic number of 19. This means that we have 19 protons and 19 electrons for all three of our isotopes. And to figure out the number of neutrons, we take our mass number, so in this case 39, minus our atomic number of 19, giving us 20 neutrons. Here, our mass number of 40 minus 19 gives us 21 neutrons, and 41 minus 19, 22 neutrons. So let's write the following elements in isotopic nomenclature. So if we take a look at beryllium, beryllium has an atomic number of 4 and an atomic mass of 9.1. So we write our symbol for beryllium, Be. The atomic number 4 goes on the bottom, and our atomic mass, 9.01, rounded to the nearest whole number, is 9. So it's 94 Be. If we want to take a look at iron having a mass of 26, or an atomic mass of 55.85, an atomic number of 26. Iron with an atomic number of 26, 55.85, rounded to the nearest whole number, gives us a mass number of 56. Zinc has an atomic mass of 30 and a mass number of 65.39. Zinc with an atomic number of 30, so 30 goes on the bottom, 65.39 rounds to 65, so it's 6530 zinc. We define atomic mass as the weighted average of all the naturally occurring isotopes. So let's take a look at how to calculate weighted average. If we look at the two isotopes of carbon, carbon-12 or carbon-14, we would expect a regular average to be 13. However, a weighted average takes into account how much of a substance is present. So carbon-12 is present in 98.8% of all carbon, while carbon-14 is only present in 1.1%. So to calculate the weighted average, we take 12 times 98.8 and 14 times 1.1%. Remember, these are percentages. You either have to enter it using the percent button or convert your percentages. So you either need to use the percentage button or convert your percent to a decimal. 98% is 0.988 and 1.1% is 0.011. So 12 times 98.8% is 11.86, and 14 times 1.1% is 0.15. We then add these numbers together and get a weighted average of 12.01. So let's calculate the average atomic mass for two other isotopes. We should assume that our final answer will be closer to 7, because 92% of our isotope has a mass of 7. So we first take the mass of each isotope and multiply it by the percent abundance. So for isotope 6, we take the mass of 6.015 times 7.5%. And again, notice I converted 7.5% to a decimal. This gives me 0.451125. For isotope 7, I take 7.016 times 0.925, and I get 6.4898. I then add those two numbers together, and I get an average of atomic mass of 6.94. And our units for atomic mass are AMU. If we calculate the average atomic mass for this last isotope, now we have 3. So we take our mass, 12.00 AMU, multiplied by our percent abundance, so 12.00 times 0.9927, and we get 11.9124. Our second mass, 13 times a percent abundance of 0.0067. Again, 0.67% is 0.0067 as a decimal. And I get 0.0871, and then 14 by 0.0006, and I get 0.0084. When I add these numbers together, I get an average atomic mass of 12.0079, or 12.01 AMU.